the last lecture we have seen the standard classic principal component analysis. And now what we want to do is we want to kernelize this algorithm and derive what is called the kernel principal component analysis, or kernel PCA. Now if you think about it, a concept like kernel PCA sounds a bit strange, because remember what the kernel approach does. And maybe I draw a figure once more, just to recap. We have some data sets that live in some original space. It might be a vector space, but maybe it's not. It could also be some other space, but here I now plot it as a vector space. Then typically what we do is we have this feature mapping that is often given implicitly that tries to map the data points to some feature space, typically the reproducing kernel Hilbert space. And then we have the data points mapped in this feature space. And then we want to apply a linear algorithm in this feature space. And in this case, the linear algorithm would be a PCA. So what we might want to do is we want to find the principal directions of the data and then project onto these principal directions. And then we might want to apply some other learning algorithm and sort of do something in between. Or like do this as a pre-processing step and then follow up with a different algorithm. And now the question is really, I mean, the whole trick is now that typically the kernel approach works like this. We now have some algorithm that does something on this linear space, and the idea is that we want to have this shortcut involving the kernel, such that we don't need to take this detour that takes us via this explicit feature space. But now what we want to do is we say we want to do PCA, and PCA is sort of the algorithm that most of all seems to need to have access to the coordinates of your data points. Because what do you need to do? For like PCA here, you need to find what is sort of the direction of maximum variance. You need to first of all find this direction, then you need to project to get rid of the other directions. For all of these things you need to have coordinates, and also you need to look at that, like if you think about how the PCA algorithm works, we look at the covariance matrix of our data, and the covariance matrix is the matrix that contains information about your coordinates, because it's a d times d matrix when d is the dimension of your space, and it sort of tells you what is the correlation between the different dimensions in your data. And somehow it seems very strange that you should be able to do something like that without explicitly having the representation of your data. And the really cool thing is that there yet is a way that works around that, and that you can do useful things with that. And in this lecture we are going to see how that works. To see where the trick is going to come from, we need to recap again what does PCA do, and also what is the covariance matrix and what is the kernel matrix. And to make it explicit, I have a recap slide here. So, assume we have data points x1, xn, and for simplicity assume they live in Rd. And also assume that they are centered, so we don't need to take care about centering the data points first. And now, as usual, we put the data points in a matrix called capital X, and we put it as rows. This is how we always do it. So our data matrix is called capital X, the points are rows. So we have n rows, one for each point, and we have d columns, one for each of the d coordinates of our points. Just to introduce some notation, we now denote the kth column of this matrix by capital X and then in parentheses k. And now I have already hinted it in the last lecture, but what I want to say now once more is that the covariance matrix of this data set is given by X transpose X. Remember, the covariance matrix tells you what is the covariance between the coordinates of your data points. If you don't know if you haven't seen a covariance matrix yet, it's time to go to your recap slides and recap multivariate statistics and look at what a covariance matrix is. So this is really important to know. But I guess you know it. So, and what I want to say now is, in this case, the covariance matrix is given as X transpose X. And I here try to make it very explicit why this is the case, because I think it's important that you really understand that point. So, what is the index KL of this covariance matrix? So we in row K, column L, what is the entry? It is the one-dimensional covariance, and I explicitly here wrote this cov1 dim because I wanted to make sure that this is really the one-dimensional covariance between the case coordinates and the else coordinates. So you now have, you restrict your data just to coordinate k, and you restrict it to coordinate L. You now have n realizations of the random variable of the case component, and you have n realizations of the else component, one for each data point. So you have, and now you can compute what is the covariance between these two sets of variables in the standard one-dimensional case, because each of these variables is just one number. And because we know the data has been centered, the covariance is just given as the sum of the products of the two entries. In this formula you should know this is the one-dimensional covariance of centered data points. And if you now transform it again to matrix notation, it is the same as computing x transpose x and then checking entry KL. So this shows why the covariance matrix is really given by this formula x transpose x. Yeah, this is more or less the same thing once more. What you always might want to check is also that what you get is really a d times d matrix. This is because, as I said, x is a n times d matrix, so x transpose is a d times n matrix. Then x transpose times x is a d times d matrix. Just make sure that all these things sort of work out. Now the other thing that you might want to look at is the kernel matrix. And if you remember, when we introduced kernels, I said the kernel matrix of the standard linear kernel is x transpose. So it's the same kind of product, just the other way around. This is an n times n matrix because x is an n times d and x transpose is d times n, so the product is n times n. And we have already seen that the kernel matrix of a linear kernel, if the data is centered, is given in this way. And if you want, you can also, again, I mean, here's the proof. If you look at entry ij of this matrix, you can now, I mean, you do the math. What is the definition of the matrix product? You just write it out. And then in the end, you end up with the fact that this is the linear scalar product between vector xi and vector xj, because this is really sort of, it's the same notation. I mean, this is x transpose, xi transpose, xj transpose is the same as the scalar product. And this here is the formula how you multiply two vectors with each other, right? So if they have d dimensions, you need to go over all coordinates and multiply them entry-wise. Okay, now what we see on this slide are now two interesting things. The covariance matrix is x transpose x, and the kernel matrix is x transposed. And this sort of should start to get thinking. Now what do we need for PCA? We need to know the eigenvectors and eigenvalues of the covariance matrix, which is x transpose x. What we have in a kernel approach is the kernel matrix. And of course we can compute its eigenvalues and eigenvectors. And that's the matrix x transpose. And now the big question is whether we can make a relation between the eigenvectors of this covariance matrix and this kernel matrix. They somehow it's the product taken the other way around. And it doesn't seem completely impossible, at least, if you look at it from this place, that there might be a relationship between the eigenvectors of C and the eigenvectors of K. And similarly for the eigenvalues. And this is sort of the main theme that we need to figure out when we want to derive kernel principal component analysis, and this is now what is going to happen on the next couple of slides. And I have a couple of propositions that try to shed light on the different directions. So we have relations from the kernel matrix to the covariance matrix and the other way around. We start with this particular proposition, which in shorthand just means eigenvalues of K or eigenvectors imply something about the eigenvalues and eigenvectors of C. And I just abbreviate it by eig. So let's first try to read the proposition. So again, we're given n points that live in Rd. This is our standard setup. And I think the points need to be centered, and I forgot to put it on the slide, or in the proposition here. We see it when we go through the proof, but I think I don't do any centering in between, so I also assume that the points are centered. And now assume we look at the kernel matrix first, K, and assume that lambda and A are eigenvalues and eigenvectors of the kernel matrix. So, we're given the data, we can compute the kernel matrix, and then now assume that A is an eigenvector of the kernel matrix with eigenvalue lambda. This means it satisfies k times A is lambda A. All this is given. Now we define a new vector V, which is just x transpose A. X transpose is the transpose of our data matrix. A is this eigenvector of the kernel matrix. Okay, and here's just a formula how this looks like. And now we make two statements. The first one is, if this vector V that we just defined is not 0, then it turns out to be an eigenvector of the covariance matrix with the same eigenvalue as we had before, which means, if you write it down explicitly, that C times V is the same as lambda V. Okay, so let us again start. We start with the data, we compute the kernel matrix, we take one of its eigenvectors, then we compute some new vector that depends on this eigenvector A, and we call this new vector V. And this new vector is now an eigenvector of the covariance matrix. And we also know something about the length of this vector. If A, the original eigenvector of k we started with, if this has norm 1, then this new eigenvector, in the way we defined it above here, this V has norm square root of lambda. Okay. For now, let's simply first of all look at the proof and later digest again what this means. So the proof, we start with the first statement, and in fact the proof is very simple. We know that k times A is lambda A because A is an eigenvector with eigenvalue lambda. Now I simply replace the formula of k with these x's. And now I do a trick. I multiply the equation that we have here from the left side with x transposed. So you can see that here, so x transpose xta is what we had in the line before. And on front we now have this x transpose. And similarly here, this is x transpose times this line. Simply I pulled lambda out again because lambda is a scalar and you can move it wherever you want to have it. Note that here we have now an imply. So previously, here this was an equivalence relationship because this was simply the definition of the kernel matrix that we used here, and that goes in both directions. Here we now just have an imply error because if I start with an equation and I multiply it on both sides with the same thing, I know that the outcome is again the same thing, so this is why we have this implication. But whether the other way works or not, we never know, because for example we could multiply with something that is 0 or whatever. It's not always clear that the other direction works, and we don't need it here. So we just have one direction. And now this last thing is now again equivalent to saying that C times V is lambda V. And why is this the case? Observe what is the vector V. V is x transpose A. It is this vector here. And then this matrix here is the covariance matrix C. And here on this side we again have the vector V. So this is what we wanted to prove for step 1, and it was really simple. We just, you just needed to multiply with x transpose from the left, and then everything sort of comes out naturally. For 2, we need to look at the norm of this vector, and this is also simple. We want to compute what is the norm of this vector V. We put in the definition. This vector V is defined as x transpose A, and if you write it down in this way, in this formula, so this is inside the norm, we now simply plug the definition of V. Now we spell out what is the norm. The norm is taking the norm squared, is the scalar product of the vector with itself. We exploit that the scalar product is linear and take out the sum and the coefficients. And now we observe that these guys here are the scalar products, which in the case of the linear kernel corresponds to the kernel here. So what we have now is this quadratic form involving the kernel, A transpose Ka. Now we know that k times A is the same as lambda times A, because A is the eigenvector of k. This is where we exploit this property. And then we know that A has norm 1. This is how we define the vector A in the part 2 of the proposition. So we can take the lambda into the front, and then we have A transpose A, which has norm 1. Squared norm 1, doesn't matter. And we are left with lambda. So what we have proved is that V, the norm of V squared is lambda, and what we have in the proposition, we just didn't put the square here. The proposition says the norm of V is square root of lambda. So this is a surprisingly simple proposition. And what it says now on the high level, if we start with eigenvectors of the kernel matrix, we get eigenvectors of the covariance matrix by this mechanism. Now observe, if we want to apply kernel PCA, we also need the other direction, because what we want to do is the PCA algorithm says we take the covariance matrix and then we compute its eigenvectors. So what we now need to look at is the other direction. We take the covariance matrix, and if we have the eigenvectors, do they also correspond to eigenvectors of the kernel matrix? Because later this is what we want to do. We want to replace the eigenvectors of the covariance matrix by those of the kernel matrix. And this is now this other proposition that shows the other direction. It's now proposition 16, and it says the eigenvalues of C imply something about the eigenvalues and eigenvectors of K. Here I now explicitly say that the data points are supposed to be centered. And now assume that V and lambda are eigenvalues of the covariance matrix. So we start with the other matrix. So C times V is lambda V. This is the eigenvalue equation. And now I again define another vector. I define the vector A. And how do I define it? I simply say you compute x times V and you multiply by 1 over lambda. Then you end up with a vector in Rn. And this might be something you might want to check, that this vector really is a vector in Rn. And the proposition now says this is now an eigenvector of K with eigenvalue lambda. So what we have is the eigenvalue equation for K. Now let's look at the proof. The proof proceeds in a couple of steps. It's a bit more, it's not complicated, but a bit more complicated than the previous proof. The first step says that the non-zero eigenvalues, eigenvectors of the covariance matrix can be seen as linear combinations of the input points. Let's see how this works. So by assumption we know lambda V is C times V, because we assumed that V is an eigenvector of the covariance matrix, so this is the equation that states that. And we know that the data is centered, hence the covariance matrix is given by this formula that we have already seen before. So now let's start. We start with V. This is 1 over lambda CV. This is essentially this equation here, which comes from this assumption. It's just rewritten. We divided this equation by 1 over lambda. So we have this equation here. Now we plug in the definition of the covariance matrix. Nothing really changed so far. We just plug in the definition. And now the trick is we need to go to this formula here. And the trick is here to see, like if you have several multiplications of vectors or matrices, you can sort of group them as you want. And I now want to, so it doesn't really matter in which, like if I would consider putting parentheses, it doesn't really matter where I put them. And I put the parentheses here, and xj transpose V is the same as xj scalar product V. And this is what we have here. It's exactly the same thing. And now we can check this here now corresponds to, if you check now what is the definition of A. A was the vector that we defined, A is the vector that is defined here. So we define this vector A in this way, such that this equation here holds. So this is, I mean, in the theorem, of course, it's stated the other way around. We start defining A and then prove that this property holds. Excuse me. Got a bit cold today. But so, of course, how you derive this proof, you start with this calculation and then you define A such that this equation is true. And it turns out that you need to define A in this way, and then you have the equation that we're looking for. So we have now, if you read from left to right, we have now V equals essentially A transpose X. And here is it's sort of, this is the formula. Okay, so this was the first step that we wanted to look at. And now the second step is we now want to express the eigenvectors of the covariance matrix with those of the kernel matrix. Let's see how this works. So again, we start with the eigenvalue equation for the covariance matrix. What we now do is we plug in all the definitions. So here we plug in what is the definition of the covariance matrix. Here is the definition of this vector v. Here is again the definition of the vector v. And now we do various transforms. So here we simply take out the sums and exploit linearity. Essentially this is sort of easy. Here we didn't change. And now comes again one step that only goes from the first statement to the second statement but not back. Again, what we do is we multiply with something suitable, and in this case we simply pick some data point s. It doesn't really matter at this point which one it is, just any of them, and we multiply with this vector xs transposed from the left side. So here we have now x transposed and the left side, and here we have xs transposed in the right side, and again I already moved the x transposed here inside this expression here. And now again you can start grouping vectors. We group it this way, that we group xs and xj here, and then we group xi and xj here. So to do this we need to move this xs inside, and we can do that by linearity. And similarly here on the right hand side we also replace this by the scalar product. And now we can replace the scalar product by the corresponding entry of the kernel matrix, because we're in the linear case. And then if you look at it sharply you will see that this left hand side here is exactly the same as k squared a evaluated at s. And the right hand side is lambda times ka evaluated at s. So far so good. So what we have obtained so far, here is sort of again a recap. So we start with this vector v defined in this way. This is an eigenvector of c. Then for each s, this is the arrow that just went in one direction, what we get is that k square a index s is the same as lambda ka index s. And in matrix notation, now we have that for all s from 1 to n, so for all coordinates we have the identity, so the identity also holds for the vectors themselves. So observe k square a is a vector of n dimensions, and the same holds here. So we have that for all, now these kind of vectors are the same. And now comes sort of one important step. We want to come to this statement here, which intuitively means we need to divide by k. What does it mean to divide by k? We need to take the inverse matrix. And why can we do that? So we need to multiply with the inverse matrix, and this inverse matrix exists because k is a positive definite matrix. And this is also where we need a kernel. If it wouldn't be a kernel, then at least we wouldn't know at this point that it's positive definite. And once we have this, I mean, this is the eigenvalue equation that we wanted to show. We can see that A is an eigenvector of k with eigenvalue lambda. Okay, so we have also proved the second proposition. So what we have now is we have these two propositions. The first proposition says, start with an eigenvector of c, do some manipulations, you end up with an eigenvector of k. And the second proposition says, start with an eigenvector of k, do some manipulations, and you end up with an eigenvector of c. So this looks really good. I wanted to convince myself that nothing goes wrong on the way, because I mean there are all these massy things going on and it's so easy to make mistakes. So maybe you might want a sanity check. Here is one. Because you can apply these two propositions one after the other. You can say we start with c. The first proposition tells me the corresponding eigenvalue of k. And now the second proposition tells me how I can convert this again to an eigenvalue of c. And hopefully the two things coincide. And here is this sort of sanity check. So we want to apply both propositions one after the other. So we start with an eigenvector of c. And we call this vector v, and the eigenvalue is lambda. We define a as in the first proposition. And know that by the first proposition then k times a is lambda a. Now we do what is said in the second proposition. We now apply x transpose A. Sorry, I switched the numbers of the propositions here. And now we apply the first proposition. The first one tells us how to go from K to C. So we do what the first proposition tells us. So we know that C times V tilde is the same as lambda times V tilde, where V tilde is this vector defined in this way. And now what we would like to have is that V and V tilde are the same, because sort of we did the circular argument. And now let's see whether this is true. The definition of V tilde is x transpose A. Now I can plug in the definition of A, which is 1 over lambda x times V. Now I can pull the lambda in front, so we have x times V here, x transpose x, sorry, which is the covariance matrix. So we end up with this expression, and this is exactly V because V was an eigenvector of the covariance matrix. So we indeed find that V tilde is V, which is reassuring. There's a tiny little thing. I mean, at least you need to make sure that this eigenvalue is not 0, and this might be something you might want to think about, and we are going to see why this might matter in a second. But sort of this first sanity check is okay, which is always good. And it's always important if you derive theorems like that, even if you just want to understand theorems like that, to do these kind of sanity checks to make sure. I mean, there could also be many typos on my slide to really make sure that that's true. I simply want to encourage you, whenever you stumble across propositions or so, do a sanity check whether these kind of propositions might make sense. And this is one of the sanity checks you might want to apply if you look at these two propositions jointly. Let's maybe also try to think about the dimensions, because this is again something that can be really confusing. So the covariance matrix is a D times D matrix. So by default it has D eigenvalues. Now K is an N times N matrix, and by default it has N eigenvalues. I mean, both these matrices are symmetric, maybe that's the first thing. So for both matrices we can in fact compute a decomposition in terms of eigenvalues. But now somehow it doesn't seem to fit quite, because we now say, start with an eigenvector of C and then you end up with an eigenvector of K, and also start with an eigenvector of K and then you end up with an eigenvector of C. But now the numbers of eigenvectors doesn't match. In one matrix we have D, and in the other matrix we have N eigenvectors. So how can this be? This is really a question I'm not going to answer in the video. I would like you to think about it and really figure out what the issue is here. We have seen a similar issue already before. Please try to figure out what really the problem is, why, or what is, if there is a problem or if there's not a problem. This is important to understand the whole concept. And you probably can't do it within a minute, so you might want to either stop the video now and take an hour to figure it out. Maybe you also know it, then it doesn't take so long, or do it later at some point. Now we want to come to the algorithms. So the first algorithm is we can now compute the eigenvectors of C by looking at the eigendecomposition of K. And this is sort of what we would know, what we would need to have if we want to use something like a kernel PCA. Let's see what the slide says. So again, we assume that we have data points that are centered in RD. And what we now want to do is say we want to compute the Lth eigenvector of the covariance matrix. Now what we do is we compute the kernel matrix of the linear kernel and its Lth eigenvector. We call it A. We make sure that this eigenvector A is normalized to A equals 1, as it also is stated in the proposition. And in most of the, like in MATLAB or R or so, typically when you do an eigendecomposition of a matrix, the result is being normalized, but maybe you might want to check that. And then we compute the vector V. Excuse me. We compute the vector V as defined in the proposition as 1 over square root of lambda. This is the normalizing factor we need to get this one to norm 1 times sum of AI xi. So this is the first step. So what this says is, if someone gives me the kernel matrix and the data points, because we still need the data points here, then I can compute the eigenvectors of the covariance matrix without explicitly computing the covariance matrix itself. And And here I have this note that is really important. So this algorithm here, as it's written, if you want to compute this vector, you still need to have the original, I mean, if you want to compute the vector v, then we still need to have these coordinates of x. So if we wanted to perform this in the feature space, then we would need to have these coordinates of our data points x in the feature space. But note that v, of course, is also a vector that lives in the feature space. So somehow, if you want to express this vector itself, there's no way you could do this without really looking at coordinates in the feature space. The trick is going to be that in practice we never want to compute these eigenvectors directly. We just want to use them to project. And to project, we again need to multiply a matrix containing eigenvectors with data points, and this in the end is going to be a scalar product again. So this is maybe what we should look at the next slide. So assume we want to project on an eigenvector of the covariance matrix. And we have already seen this kind of expression a couple of times on the slides. So now how does the projection look like? The projection on the vector v of some other data point xi, I mean it's defined as v transpose x, and now we can plug in the definition. And sorry, v transpose x, you can also write this as the scalar product of v with xi, sorry. So here we have the scalar product, and now we also replace the vector v by the definition here. And this is now a sum involving coordinates of a, or the vector a, which comes from the kernel matrix, and the scalar product xj, xi. And the scalar product, again, we can sort of do, this is our kernel value. So if you, so this is the first statement, and this is just for one vector, but if you want to project on an L-dimensional vector, of course the same kind of principle applies. So the previous formula just shows it how to do it in a one-dimensional subspace. For an L-dimensional one, sort of, you can more or less do the same. For example, do it like for dimension 1, dimension 2, and dimension 3, and so on. So you can see that it essentially works. So the big thing is, again, to compute these projections, we only need scalar products. And the projection is all we're interested in the end. So we can do the kernel PCA. We can sort of do this as a kernel algorithm, and it's going to end up in kernel PCA. And here's now the algorithm. So the input of the algorithm is only the kernel matrix that has been computed from our data points and the parameter L. So what we do first is we center in the feature space, because most of the computations we did were assuming that the data is centered, so better we do that first. So we center our feature, and we have seen how that works. So we center in the feature space. Then we do the eigendecomposition of this new centered kernel matrix. We let AK denote the kth column and lambda k the kth eigenvector, eigenvalue. Then we define this matrix VL, which we need to compute the projection. And this matrix is simply these original vectors A divided by square root of lambda k, which we needed to normalize them to norm 1. We do that for all k between 1 and L. And then we can compute the low dimensional representations of the points with this formula. So here is for all, so I really did it explicitly here, for all s between 1 and L. So s is now the coordinate, the s coordinate in the low dimensional space. You can compute the formula with this way just by using the sum over so this is sort of the standard formula that's just spelled out for individual coordinates. And then you can do that for all data points, of course, and then your output is the new points, and they live in RL. And this is something that's really cool, and maybe I want to go back once to the iPad to say yet again why this is really cool. Sorry. So we start with this abstract data points here. These can be points that already live in some Euclidean space, or it can again be something very abstract like molecules. What we want to do is implicitly we do this feature mapping that takes us to the Hilbert space, or to the high dimensional space if you want. Have a representation here, sorry. So this is maybe how the points look like in this high dimensional space. Now we do a PCA in this high dimensional space. So for example, say we do a PCA on one dimension, we project on this particular line. So all the points end up on this line. And what we return is essentially the representation of the points on this one-dimensional line, right? So this is what we do. So we do PCA in the original space, and the projection and the output of the algorithm is going to be this projection. So here these are the projected points. And they live in RL, where L is this parameter that we choose, the dimension of the vector space. And now the really cool thing is that, again, the kernel trick works here. So you can do this, all this implicitly by doing this computation on the kernel matrix directly, and you end up with a low dimensional representation of your data points in RL. And this, I find this very, very surprising. I mean, of course I know it, but it's sort of, if you wouldn't think that something like this works, because PCA is something that is so inherently tied to coordinates that it seems very surprising that it works. I want to make one more remark here, and the remark is that now also something funny can happen regarding the dimensions. So assume, for example, our original data, say it lives in R2. Two-dimensional data set. Now we use a Gaussian kernel, say. I don't write it here. So we just consider we use a Gaussian kernel and do a feature mapping in the reproducing kernel Hilbert space. For the Gaussian kernel, typically if you embed n data points, no matter from where they come from, after embedding them into the RKHS, you have an n-dimensional subspace. Each point spans its own direction. So now, in the case of the Gaussian kernel, this space is Rn. So it's a reproducing kernel Hilbert space, but just n of the dimensions. So it's an n-dimensional subspace of a Hilbert space. This is isomorphic to Rn. And n is now the number of points. And here we started with R2. On the left-hand side, we had just 2 dimensions. Now I'm in Rn. I can do PCA in Rn, and I can decide maybe I want to embed on a 10-dimensional subspace. So then here this RL in the bottom of the plot might, for example, be R10 now, because I decide that L is 10. So what happens now is that if you go from the original data directly to this kernel PCA, you in fact even increase the dimension, because we started with 2-dimensional data and the output is 10-dimensional data. So by doing this detour of the kernel trick, we would not reduce the dimension. In this particular case, we can even blow up the dimension. And of course, the question is whether something like that would make sense in practice. And there can still be cases, because sort of the kernel does this very complicated nonlinear transformation between your original space and this Hilbert space. And maybe in the Hilbert space you have a good structure that now if you reduce it to, say, a 10-dimensional space, still helps you in your data. So it can make sense. And we are going to see an example in a minute in a demo where in fact something like that can happen. Okay, I now want to show you this MATLAB demo for kernel PCA for a couple of toy data sets. And we start with a funny data set, which is a 2-dimensional data set just consisting of concentric rings. And let me try, this is the original data set. So it's a 2-dimensional data set, and I just colored these rings in 3 colors to be able to see what happens to them. So this is simply a toy data set. And now we can apply different algorithms, different PCA algorithms to this. So for example, let me see, we can do kernel PCA with, now and we need to see which kernel did I choose here. The kernel matrix is the Gaussian kernel, as you can see here. So, I mean, it's always important which kind of kernel do you use. I use the Gaussian kernel, and the kernel width that I defined for this data set here is sigma. Oh, sorry, this is a huge sigma. That doesn't make sense. So look at the data set. Maybe let's go through it more slowly. So here, the scale of these data sets is something, I don't know. It goes from -5 to +5 or something like that. So what would be a good kernel width? The kernel width should be something like, the intuition I always have is, so if these maybe are 200 data points, you should have the kernel width such that the sort of 10 closest neighbors are safely within sort of this bell curve that is useful for your, that sort of is given by the Gaussian kernel. So maybe you might want to have a kernel width here that is goes from this maybe 1 or 2. So maybe I choose kernel width sigma is 1. Sorry. And then we apply the algorithm. Let's see. Oh, okay. Now something funny already happens. Again, so this is our original data. I now have kernel width sigma is 1, which means that points are considered similar to everybody who has more or less distance 1 or 2 from each other, and beyond that it's sort of considered unsimilar. In particular, points on this blue circle are all more or less considered similar, maybe except here there might be a gap where in fact these 2 points are not really similar anymore. Points between blue and green line or green and red lines would not be considered similar because the Gauss curve is so small that they wouldn't sort of touch each other anymore. Now what happens, I can apply 2-dimensional Kernel PCA, and this is the outcome that we get. And admittedly this would be nothing that I could ever have predicted. My guess is what happens here, this blue line sort of is now an opened line, it's not a closed circle anymore, and this is exactly, my guess is that this is because we have this little gap here. That, or maybe it's also the gap down here, it's a bit unclear. So if you would, I'm going to repeat it in a minute with a slightly larger kernel width, then maybe these gaps don't occur. But you can also see the red circle is sort of still there and the green circle is somewhere there. And admittedly, I wouldn't be able to predict that at all, that this kind of result happens. Observe, we go from a 2-dimensional space, again to a 2-dimensional space. But because we have the kernel, this nonlinear transform in the middle, something happens. So if you would do a classic PCA on your original data set and embed in the same dimension as your data, of course nothing changes. But here in this kernel approach things can change. This is what we can see here. And now I want to show you, sorry, this doesn't make sense. Where is the figure? 3-dimensional PCA. This is now the 3-dimensional embedding that you would get. So this is a bit funny. What we would see is now if, for example, you would try to apply a linear classifier after this embedding, the red circle, if you would look in this direction, you could easily fit a hyperplane between the red and the green part. The green and the blue one would be hard to separate. My guess is now, and we are going to try it, I haven't tried it before, but I hope it works. If we now choose the kernel width a bit larger, maybe 3, let's see. So what would happen then if you would choose the kernel width equal to 3? No, I'm not sure, because then here probably these 2 different rings would also already be considered as similar, but we are going to see. So here is the one I'm interested in. So what you see now is, and this is something really cool and surprising and somehow also something that I would never ever be able to predict, that you now do an embedding in a 3-dimensional space, and all of a sudden the set of concentric rings gets separated. So essentially what you do is you go to this high-dimensional nonlinear space, you go back to 3 dimensions, but it looks like now you have added 1 dimension to your data set, and this dimension seems to split these different concentric rings. We can also try play a bit with sigma. So if we now increase sigma to 10 or even 100 as we had it before, this is of course a value that is ridiculously large. And then the question is really what happens. I mean, it seems that it still works. And probably this is true because even the small variations that you get in these different kernel values are enough to sort of separate these structures. But as I said again, this is nothing that I would ever be able to predict. It could also have happened that in this data set nothing interesting happens. So I find it just curious that this happens, but I don't really understand why, or I didn't try to understand the geometry behind these things. Maybe one more thing, if you plot the eigenvalues of the kernel matrix, here we will see that it's 2 or 3 little points which indicate eigenvalues that are larger than 0, and the rest is more or less 0. So maybe you can also think about why this is the case. This is related to the question we had previously, how it can be that the different numbers of eigenvalues and eigenvectors of the covariance matrices and kernel matrices still match. So here we have 2 or 3 eigenvalues that are non-zero and the rest is 0. This is the point I wanted to make. I want to show you maybe the demo. I also have a couple of other data sets here, just for curiosity. And my Emacs currently doesn't do what I want. This is why I need to do it in an inconvenient way. Uncomment region. So here I now have this Gaussian data set that we have seen before. Let me just show it. Oops. So this is now the Gaussian XOR data set, the 2-dimensional data set. The original data set is this one. It's 2-dimensional data. You see essentially a mixture of 4 Gaussians arranged like on a checkerboard. And now you can apply, for example, 3-dimensional PCA, and it gets projected or projected is maybe a funny word. In this case, it ends up in a high-dimensional space, and it has this funny kind of saddle shape. But what is really cool is also, if you now imagine you would like to do a classification algorithm and maybe separate the blue points from all the rest, you could do that. So there would be by a linear algorithm. So if you now would apply a linear algorithm, you sort of can now find a hyperplane that cuts more or less here, and it would separate the blue and the rest of the class. You can also, I mean, this would be something that you might even be able to do in your original data as well, because you could say you sort of try to cut off this one particular corner here. But now, for example, if you say the green and the blue points should be in one class, and the pink and the red points should be in another class, this would also work, because here you have now this funny saddle shape. So if you put it like this, you could now sort of do a horizontal line and separate the green and the blue point after from the pink and the blue and the red points. And sort of it shows you that after applying this kernel, so it's again a Gaussian kernel, I imagine, with, let me check the kernel width. So the sigma of the kernel width is chosen as 0.5. This sort of makes sense. It's sort of this kind of distance here. And it means that if you go to the kernel space, then you can solve this XOR classification problem, which otherwise you wouldn't be able to solve with a linear algorithm. And this is sort of shows, it gives you an indication why this is true, because if you look at the first coordinates or the first principal components, it already gives you all the information that you would need. Let's see, I think I have one more data set here. This one. It's a 2 moons data set. We're going to see it in a minute, and just already note that sigma is 0.5. No. So the original data set is this one. This is a standard toy data set that's used all over the place. Just a 2-dimensional toy data set which has a nonlinear structure, and you want to see whether, I don't know, clustering algorithm or classification algorithms are able to do that. So this one moon is supposed to be one class, the red guy is supposed to be another, the other moon is the other class. And now let's see how this 3-dimensional PCA looks like. It also does something funny. You can see it if I rotate it. And again, you could now apply a linear algorithm and sort of cut here, and you would be able to separate this black and the red guys. Again, consider the kernel width is sort of 0.5. This is something that makes sense. 0.5 might be even considered a bit large, because here you would get connections like points. For these red points might be still be considered slightly similar to those red points. But I think it still works, because the similarity is not close to 1, it's maybe 1/2 or so. So it is still going to work. We can maybe see what happens if we change sigma. Maybe let's put sigma to 0.1 here. Now something completely different happened. So sigma is now, again, look at it's 0.1, so 0.1 is really small. This means everybody is maybe similar to his nearest neighbor, but not more similar to anybody else. This often means that you start to lose all of the global geometry of your data, because for example, I mean, this point here isn't going to be similar to anything else. What happens now, and again, I want to say that I would not be able to predict this, but this is sort of the outcome. You would have, the red moon is going to project it on this guy here, and the black moon is going to be projected on this guy here. for whatever reason. This is the secret of kernel PCA and the kernel geometry. I can't predict it, but this is simply what happens. We can also check the other way around. If you do sigma maybe 2, that's really large for this data set. Let's see what happens. In this case, we get this kind of structure, which now means that if we wanted to apply a linear algorithm, it's not so easy anymore. The structure doesn't seem, at least the fact that we have now 3 dimensions doesn't bring out anything new in the data set. It more or less leaves the data set a bit like it is, it just curves it a bit. And again, so the sigma was 2. If we go now to this plot, sigma is 2. This means that everything between 0 and 2 is really considered similar, and even between 0 and 3 or 4 is considered similar. So it means also that these bridges are not going to be separated anymore. So you would have sort of bridges between the black and the red set. And this is maybe why at least it's not considered so dissimilar anymore, and in KPCA maybe it ends up in this way. But again, I want to stress, this is nothing I would be able to predict, that if you choose sigma in a useful range, that then something interesting happens to this data. This is just something that you can try in practice, and sometimes it works and sometimes it doesn't. So let me summarize. We have looked at the kernel PCA algorithm, which tries to bring the standard principal component analysis in the kernel space. The mathematical mechanism that we needed to invoke is that the eigenvectors and eigenvalues of the covariance matrix are can be expressed in terms of the eigenvectors and eigenvalues of the kernel matrix. And this is done there are simply math equivalences why this works. What happens geometrically is you take your original data, put it in this very high dimensional space with the kernel approach, at least if you use something like a Gaussian kernel, so you end up in this high dimensional space, and then in this high dimensional space you apply a projection that then brings you to some low dimensional space RL. And by the kernel approach you can do this direct link without going this detour over the kernel space. You can do the direct algorithm, which means that you start with any arbitrary data set. It could have a Euclidean structure, but even doesn't have to, so a set of molecules. And you end up with a representation in RL that hopefully describes your data set in a nice way. And sometimes in practice it is going to help you, and sometimes it is not going to help you, and there is no, in many cases you can't really predict it, but you can always play with it and try it. And if it does help, then simply add it to your pre-processing chain. Maybe to look a bit at the history of PCA and kernel PCA. So the classical PCA was invented by Pearson. We have seen this person before. He is one of the fathers of statistics. In 1900 something he worked, and there are a couple of papers around this area. So this is the original paper, 1901. That's 120 years old. That's really cool. And as I said here, it's one of the most popular classical mechanisms for data analysis. Everybody who works with data, be it in biology, psychology, physics, everybody knows, who works with data knows PCA. Sometimes they know it under different names. There might also be slight variations, but the principle is always the same. And now the kernel PCA was invented more or less exactly 100 years later, namely 1999. By Bernhard Tschirkow and Alex Moeller and Klaus Robert Müller. That was in the rise of the kernel kind of algorithms. We have seen the support vector machine. It was invented a couple of years earlier, the kernel version, I think 1996. And that was when everything started. And then this is again yet another breakthrough in the field of kernel algorithms, because this is something that is really surprising and also cool that you can do that. So it was published 1999. And I guess many of you know Bernhard Tschirkow. He's in Tübingen as well. Yeah, I think that's, here's my summary, but I already did a summary earlier, so I don't need to repeat the summary. Maybe just to say that kernel PCA is really an important algorithm, both conceptually, but also to understand how kernelizing works, and maybe also to show that it's not always so straightforward to kernelize an algorithm as for the SVM, where we just see, oh, there is scalar product, we replace them. Sometimes you really need to invest quite some work.